You give an AI a complex, multi-step task. It chugs along for a few seconds, hits an error, and completely stops in its tracks. To get it moving again, you have to read the code, copy the error message, and paste it back into the chat box. You become the system's eyes and hands. A large language model acts as a raw prediction engine. It processes the text you provide to mathematically calculate the next word in a sequence, a process that repeats one token at a time. As long as a human has to sit at the keyboard, watching the output and manually feeding errors back into the prompt, the software isn't autonomous. You are. To understand this limitation, we have to look back at the machine that built the modern world, the industrial steam engine. A steam engine operates on a simple one-way power chain. It burns fuel to push a piston, one discrete stroke at a time. An LLM operates the exact same way. It burns tokens, small chunks of text, to push out one word at a time. But raw power has a dangerous flaw. If the physical workload on a basic steam engine suddenly drops, the engine will spin out of control. It has no way to observe its own speed. It is entirely blind. Throwing more computing power at an AI model doesn't make it an independent worker. A massive engine that cannot govern itself is just a faster way to crash. 240 years ago, the engineer James Watt faced this exact problem. His steam engines had the brute force to power entire factories, but if the machinery shifted, the engines would accelerate violently and tear themselves apart. The mechanical solution to this problem was a device called the centrifugal governor. The governor is driven by the engine's rotation. As the engine speeds up, centrifugal force pushes these two metal spheres outward. That outward swing physically pulls a lever, which chokes the steam valve, slowing the engine back down. The machine observes its speed, feeds that measurement back to the intake valve, and corrects itself. It operates safely without a human standing over it. Modern AI agents are built using the engineering blueprint found in the mechanical steam governor. By looking at these two systems side by side, we can see how code mimics iron. When an engineer adjusts the governor, they set a target speed, a set point. When you give an AI its system prompt, you define the exact goal you want it to reach. The governor's only method of affecting the physical world is to adjust the steam valve. An AI agent's method of affecting the digital world is calling a tool, like running a Python script, creating a file, or searching the web. And just as those metal flyballs detect the engine's actual speed, the output of the AI's tool, whether it's a successful web search or a hard code error, is fed right back into the model's text window. The AI observes the physical results of its own actions. This mapping reveals that the intelligence of an agent is separate from the language model itself. The model acts as the blind piston, while the feedback loop provides the capacity to act, check, and correct. But what happens if you command a self-watching machine to just keep working, without mathematically defining what finished looks like? If you boil a pot of water and walk away, it eventually boils dry. Early steam engines faced a similar failure state called Hunt-in. If the governor was calibrated poorly, it would overcorrect, swinging wildly back and forth in a violent mechanical stutter. An AI agent without strict boundaries does the exact same thing. It gets caught in an infinite loop. It will endlessly rewrite the same block of code, hallucinate new errors to fix, and quietly burn through thousands of dollars in computing costs. A system that continuously corrects itself will eventually destroy itself, unless it is forced to stop. In 1868, the physicist James Clerk Maxwell wrote a paper titled On Governors. By using differential equations to map out exactly how to stabilize a steam engine, he founded the mathematical field of control theory. Today, software developers practice the modern equivalent, loop engineering. They design the safety guardrails and the strict termination conditions required to force a chaotic AI loop to converge on a final answer. The hardest part of building an autonomous system isn't getting the engine to start. It is defining the exact criteria for when it must stop. We have successfully built a cognitive steam engine. It processes information at a scale we can barely comprehend. Our ability to safely use that power now relies entirely on our mastery of the loop.